Hello, today we're going to be talking about programming languages. These are computer programming languages that have evolved over the history of modern computing since basically since the 1950s. So let's get jumping right into this. Here we go. Here's the talk coming up here. And now I'm going to go to this. And everyone should be able to see this here. There's a graphic here showing these are just some of the many, there's hundreds, probably even thousands of computer programming languages that have been developed, invented, whatever, since the 1950s. And this is just a snapshot of what they are. So here we go. We're going to start with just setting terms so we're all on the same page. What is a programming language? And then we're going to talk about procedural programming, which is basically where a lot of people started from in the 1950s and 60s. They had a procedure. You do A, then you do B, then you do C. So the program was coded as a set of procedures. First, you do A, then you proceed over from A to B, then you do B, and so forth. And what wasn't obvious was that this led to some real problems when you wanted to change the program. This is what we call the test problem. As these programs got out there and people liked them, they were written in these particular programming languages in a procedural manner. The test problem was that they would go ahead and add features, but then they have to go back and test to make sure that everything still worked, not only the new features, but the old features, and that there were no problems here. And over time, as more and more features got added, it became clear that the test time was just blowing up exponentially, and something had to be done to fix this. And so in the 1970s and 1980s, a group of people realized one way to address this was through what's called object-oriented programming, where we'd solve the same problem, but what we would do instead of following a procedure is we'd have a set of objects. So one might be a calculator, one might be a data gatherer, and one might be a display. And so these objects would interact with one another, say by sending a message back and forth. So we'd send a message to the data gatherer and it would gather data. And then it would send a message to the calculator who would calculate whatever. And then that would be sent to the display where graphs would be displayed and so forth. But it was all done by messages. And each of these objects was self-contained. And so if any changes were made, you made the change to the object that was there, and therefore you knew that there were no problems with the other objects because the only objects you had to worry about were the ones that had changes made to them. We'll then go into Al Aho, who's one of the giants here in all of this, and touch upon his contributions, not to lose sight of this. And then we'll run through a historical survey of programming languages. Again, here's a graphic over here to just give you a taste for how many programming languages there are. Okay, here we go. A programming language is a system of notation for writing computer programs. So the programs have a syntax or form, and their semantics or meanings that are usually described through a formal language. And the languages provide features such as setting types of systems. You could have integers, you could have floating point numbers, which is another way of saying you're trying to approximate a real number with a decimal of some sort, and so on. So you can have types, you can have variables, and you can have mechanisms for error handling, which is critical for any of these things. So in implementation of a programming language is required to execute a program. So there's either got to be an interpreter or a compiler. We covered this before in a separate talk, so I refer you to that. But the interpreter is going to directly execute the source code line by line. The compiler will go through a series of steps to come up with an executable program, and then that will execute. Typically, it'll execute much faster than the interpreted version, but that's really the only difference here. And then we're going to talk programming languages are classified as imperative, functional, logic, object-oriented, and on and on. Many in the popular programming languages are combinations of these things. They're both imperative, or as we said, procedural, and they're also object-oriented. Both these things are supported. So it's really up to the implementer to pick and choose how they choose to do things. The programming language theory is a subfield of computer science that studies the design, implementation, analysis, characterization, and classification of programming languages. We'll come back to this. The term computer language is sometimes interchangeably used with programming language, but one usage describes programming language as a subset of computer languages, that is, languages used in computing that have a different goal than expressing computer programs are generically designated computer languages. So we can have a markup language referred to as computer language to emphasize they're not meant to be used for programming. So one way of classifying computer languages is by the computations they're capable of expressing as described by the theory of computation. The majority of practical programming languages, all the ones we'll deal with here, are what are called Turing complete, and all Turing complete languages can implement the same set of algorithms. There's just an issue of style, if you will, and practical real world considerations that are into why you would choose one over the other. So we have SQL 92, SQL, and Charity are both examples of languages that are not Turing complete, but they're often called programming languages. Some authors simply restrict the term programming language to Turing complete languages. There's another usage here regarding programming languages as theoretical constructs for programming abstract machines and computer languages as the subset thereof that runs on physical computers. So John Reynolds emphasized this formal specification languages are just as much programming languages as are the languages that are intended for execution. And the textual and graphical input formats that affect the behavior of computer are programming languages. Despite the fact they're not typically Turing complete, and so it goes. Procedural programming is a programming paradigm, which is also classified as imperative programming, that involves implementing the behavior of a program by a set of procedures, also known as functions or subroutines, that call each other. So the resulting program is a series of steps. We call subroutine A, then we call subroutine B, then we call subroutine C, and they each have different inputs and generate different outputs. The first major procedural programming languages appeared in the middle 50s. They include FORTRAN, ALGOL, COBOL, PL1, and BASIC, and Pascal and C were published in the 1970 to 72 timeframe. We'll come back to all of these. The computer processors provide the hardware support for the procedural programs through a stack register, and there's instructions for calling procedures and returning from them. And the hardware support for other types of program is possible. For example, there's a Lisp machines or a Java processor, but these hardware supports really haven't been commercially successful to the best of my knowledge. So when programming languages were first developed, this leads us into the test problem here. It was felt that software application program would be developed, and over time the software would be enhanced as more and more features or capabilities were identified as needed or necessary, but the hardware wouldn't change. In fact, what's happened is exactly the opposite. When you get a critical mass of new features that result in a so-called major new change or new release of this application, it was discovered that the time required to test all the new features to ensure no problems, the old features, led to more and more time spent in testing with each new release. So I just tried to quantify this here by just showing we have a program that has 10 states, and that can be 10 factorial, or 3.6 million states that this can be in. And if the first new release only had 2 states the program could be in, then the test had to, we add two new states to this, then we go from 10 states to 12 states. So the number of states increases now from 3.6 million to 479 million. And the test time required increases from, say, 1 second to 132 seconds. If we add yet another set of features with 3 new states, then we now have 15 states who could be in, which is 367 trillion states. And you can see that it would take over 100 hours based on this illustrative analysis to do this. And this just simply gets to be unacceptable. So with object-oriented programming, if there's 10 states, we can test each of the modules. One has 4 states, one has 3 states, one has 3 states, total of 10 states. If we add 2 states, say we go from 5 states, 3 states, 4 states, then we know which modules have to be tested, and the test time it takes longer, but we know exactly where to go, and it's not unacceptable. So this was really a sea change in programming, object-oriented programming, in terms of how you design programs and structure them. And the key thing here is what the set of objects that you had. So when I was at Bell Laboratories, we developed an object-oriented PBX, private branch exchange. So what this was it was meant to be the next generation, if you will, telephone system, but the terminal that was there actually could support voice, data, video, graphics, and speech, and it could also end up, if you only had hardware that could do a subset of that, say the hardware could only do messaging and speech, it would default to that. It wouldn't crash. But all the so-called stubs or placeholders were in place so that when you ended up with hardware, for example, that could support a screen with a bitmap graphic display, then you know exactly where to go handle this. However, if you designed this thing at the get-go just to handle voice, then you had a problem because you had to go back and redesign the object, and also the messages that went from this object to the other objects to carry out your task. So this is the crux of it, is you live and die by those interfaces, by the message as they get passed from one object to another. And how rich did you make the set of objects so that as things evolve, you can handle new changes in a relatively straightforward manner. We have languages today such as C++, Java, and Python that support both procedural or imperative and object-oriented programming. And this is the par for the course, and this will continue this way for, I'm sure, quite a while. And there's a lot of just purely object-oriented languages out there, such as C#, Ada, Logo, MATLAB, and so forth. So we'll come back to these as we get into it. The terminology invoking objects in the modern sense, object-oriented program, actually was done at the Artificial Intelligence Group at MIT in the late 1950s and early 1960s. The problem they faced was that the hardware couldn't really support message passing in a manner that was speedy enough so that the delays from sending messages from one object to another were not noticeable. The hardware had to catch up with this software idea, and that in fact is what's happened. The objects that this group was dealing with were things that were encoded in Lisp, the Lisp processing language, and MIT also developed a sketchpad that Ivan Sutherland ran with, which was again a display, a sketchpad, but the software that supported this was in fact object-oriented, and so forth. This shows you that these ideas have been around for quite a while, but it takes time for people to realize that these abstract ideas would be in fact useful for anything. Another example was Simula, which was introduced in the late 1960s and was entirely object-oriented and allowing you to do physical modeling or simulations of a variety of things. Such example that I've got here is moving ships through cargo ports. So you have to load and unload the ships. So in 1966, Alan Kay began working on these ideas that eventually would be incorporated into Smalltalk programming language, which was object-oriented. And Kay used the term object-oriented as early as 1967, and this is one reason why he's called the father of the object-oriented programming. But in fact, what he had to say was, I thought of objects being like biological cells or individual computers on a network, only able to communicate with messages. So messaging came at the very beginning. It took a while to see how to do messaging in a programming language efficiently enough to be useful. This again was the crux of it. And this comes from a 1976 MIT memo. But when we get into the early 1970s, Xerox created the Palo Alto Research Center and recruited Alan Kay to go there. And he worked with Dan Ingalls and Adele Goldberg on Smalltalk, which was this object-oriented programming language. It was dynamically typed. Types could change. And at first it was written to be interpreted, not compiled, because the hardware simply was not capable of giving you adequate hardware support. The Smalltalk became noted for all of this work, and it led to graphical development. The Xerox PARC people developed a workstation, a personal computer that was had a bitmap display and a mouse and a file system with folders on the desktop. All of this was revolutionary at the time, and this led to this being running around elsewhere. So finally, Xerox didn't really exploit this, so Adele Goldberg edited the August issue in 1981 of Byte magazine, which was a premier magazine at that point for anything related to computer hardware software, and introduced Smalltalk and object-oriented programming to this very large audience that they were simply not familiar with it. And this led to a huge amount of activity, which has continued to today. And we see this happening in all kinds of applications. Intel attempted to build hardware to support object-oriented programming. It was so-called, became the Intel IPX 432. It was not commercially viable, and Intel ended up dropping it. In the mid-1980s, in an object-oriented version of C, Objective-C, was developed, and other people such as Burr and Strostrup, who used Simula, created object-oriented C++, which we'll get to, and so you see it starts to take off. It's going everywhere. It's not just in the US. At the ETH in Zurich, Nikolaus Wirth and his colleagues investigated this sort of activity with Modula 2, and they carried out a variety of tests and features with this, and so object-oriented features have now been added to previously existing languages that didn't really include this sort of capability, including FORTRAN, which we'll come back to, but also BASIC and Pascal and COBOL. And so this led to all kinds of problems in terms of compatibility and maintaining software. If you had these extensions and you wanted to use old existing code plus this new code, people discovered it was not that easy to make it all work and maintain it. There's typical of this is Python and Ruby that are both compatible with procedure-oriented methodology, but also object-oriented. So we have object-oriented programming uses objects, but not all the associated techniques and structures are supported directly in the languages. And that's because there's a notion of exactly what an object is. And this led to a comparison in the comparison of object-oriented programming languages to other things such as relational databases was very difficult because there was a lack of an agreement on what object-oriented programming was. It was clear the relational databases had a huge amount of work done, and this has led to a clarification now of what really is an object-oriented programming language, which we'll see, and that there are things that are shared with non-object-oriented programming languages include variables that store the information in a set of data types. And then there's procedures or functions or methods or routines or that take the input, generate the output, and manipulate the data. So it's these things that are shared, and the notion of modularity, anything can be made modular. That's not the point. The point is, as I pointed out before, is being able to isolate changes so that you can, among other things, know where errors might arise and contain those errors so that it doesn't impact the whole system, and you can recover from those errors in a rapid and graceful manner. So, as we said, objects sometimes correspond to things found in the real world. It could be a square, a circle, a menu, and so forth. Or it could be very basic stuff in computing. We have 4 elements for hardware. That is, we have processing, storage, input, output, and switching, a communications fabric that connects everything. And so we could have a virtual processor, virtual memory, or virtual storage, a virtual input-output, and a virtual switch, for example. That would be a perfectly valid set of objects that we could build things on. And so it goes. Now, we're going to discuss briefly Al Aho, who graduated from Princeton with a doctorate, and in 1967 went to Bell Labs, where he was there from 67 to 91, and then returned back. He went to Bell Communications Research and then came back from 97 to 2002. But he also has gone to Columbia, and he served not only as a faculty member, but was chair of the department multiple times. So in particular, in his thesis, he created the notion of index grammar and the nested stack automaton as vehicles for extending the power of context-free languages, and retained many of the decidability and closure properties of these languages. This in particular, of this application of index grammars, is to model parallel rewriting systems that might be in computing or in biological applications or many others. He, at Bell Labs, developed a very efficient regular expression and string pattern matching algorithm that were implemented in Unix as tools called egrep and fgrep. And the fgrep algorithm has been known as the Aho-Karasik algorithm. It's used in bibliographic search systems and many other applications. He also worked with Steve Johnson and Jeff Ullman to develop efficient algorithms for analyzing and translating programming languages. So Steve Johnson used the bottom-up parsing algorithms to create a syntax analyzer generator, which was called YAC. YAC stands for Yet Another Compiler. And Mike Less and Eric Schmidt, this was a summer job for Eric Schmidt, who was a student undergrad at Princeton at the time. And Eric went on to become with Sun Microsystems, and then was with Google for many years. And you see him in the press all the time. So Mike Less and Eric Schmidt used Aho's regular expression pattern matching algorithms to create a lexical analyzer generator called Lex. And so if you use Lex and YAC, then typically what happens is that any computer that you find today has a C compiler on it. That's how the evidence of the popularity of C, that statement says it all. But you might have some other language that you want to put on this, where you simply use YAC and Lex, and you have on top of your C compiler, you have another language there, which is your favorite language, and you're up and running in no time whatsoever, focusing on what you want to do. This is an incredibly powerful thing. It's used day in and day out by engineers everywhere. Aho and Ullman also wrote a series of textbooks that codified the theory relevant to compiler design. So there was a 77 textbook called Principles of Compiler Design, had a green dragon on the front cover, and so it became known as the Green Dragon book. In '86, Aho and Ullman were joined by Ravi Sethi at Bell Labs, and they created a new edition which had a red dragon on the front. And if anyone saw the 1995 movie Hackers, they showed this red dragon book there. And then in 2006, Monica Land joined in, and they created the Purple Dragon book. And these are really the standard books on compiler design for languages. But this wasn't all. Al Aho, John Hopcroft, and Jeff Ullman wrote the design analysis of computer algorithms, codifying some of their early research on algorithms. And this became one of the most highly cited computer science books for decades, and stimulated the creation of algorithms and data structures as a central course in computer science. This is really the science in computer science, is these algorithms that were developed here. They wouldn't have come about any other way. Finally, Al Aho worked with Peter Weinberger and Brian Kernighan, and so they took their first letter of their last names, A for Aho, W for Weinberger, and K for Kernighan, and they came up with a programming language, awk, which allows you to easily code all kinds of things in a big rush to have a quick and dirty implementation. And the result of this is Al Avo is probably the most widely cited computer scientist on planet Earth. Now, we're going to go into the languages, so let's start at the beginning. Here we have a picture of John Backus. He developed FORTRAN, a formula translating system, FORTRAN, and this thing is was meant to be compiled. It was meant to be imperative or procedural, and it was really targeted after numeric computation and scientific computing. John Backus developed this at IBM starting in the early 1950s, and it surfaced as a product in 1958 and just took off from there. Had very little competition, and is used for example, you see benchmarks of high performance computing or so-called supercomputers. There's a set of benchmarks that are written all in FORTRAN, and whoever runs these the fastest, that whatever that time is determines your rank in how fast you are as a supercomputer. There was also IBM developed a supercomputer called Blue Gene in conjunction with Argonne National Laboratories, and that ended up using FORTRAN and was part of this genome sequencing activity. So FORTRAN has evolved over all kinds of dialects, everything else that happened here. There's a major new version that came out in 1977 called FORTRAN 77 that supported structured programming, array programming, modular programming, you name it, it's in FORTRAN. And so if we just take a look back here, John Backus submitted a proposal to his superiors at IBM to develop a more practical alternative to assembly language for programming the IBM 704 computer. And they ended up getting this all done in 1956, and there was an actual reference manual issued, and the rest was history. Pretty much every computer on planet Earth has a FORTRAN compiler. Backus said during a 1979 interview with Think, which is the IBM internal magazine, that much of my work has come from being lazy. I didn't like writing programs. So when I was working on the IBM 701, writing programs for computing missile trajectories, I started work on a programming system to make it easier to write programs, which was FORTRAN. And scientists adopted this for all kinds of numerically intensive programs, and the rest was history. By IBM putting this out there and having all these third parties writing applications, the competitors to IBM themselves started to put out FORTRAN compilers so that they could have access to this body of applications. Now, when we go and leave FORTRAN, we go into PL1, you have to realize IBM had decided as a corporation to move to the so-called 360 line of computers, which had a common architecture, but different hardware implementations. So it spanned about a factor of 50 from the smallest, slowest to the largest, fastest. And there were a number of models, different models here, Model 360, Model 20, going up to Model 360, Model 90, and on and on. So what happened was IBM being IBM, decided to develop its own programming language, and they called it Programming Language 1, or PL1. And this was meant to be the language that would not only do scientific and engineering, such FORTRAN was aimed after, but also business and system programming types of activities. And the main thing that happened here, PL1 supports recursion. At the time, FORTRAN didn't, and all kinds of very clever linked data structure handling and different types of characters. So it's very English-like, but is incredibly flexible or powerful. The goals of this were to have performance of compiled code competitive with that of FORTRAN, but apparently this was never achieved because in part of all these features that were in PL1 that weren't in FORTRAN, it was supposed to be extensible to new hardware, new application areas, and improve the productivity of the programming process, and be machine independent so that you could run on any computer hardware base that was there. As we touched on before, the tools were becoming available so that you could in fact put PL1 on any computer using Lex and Yak, for example, if there was a C compiler there. And so what happened was there was a whole variety of data types, dynamic extents, context, concise syntax, all kinds of iterative processing. There's part of the problem with PL1, why it never really took off, was it had too many bells and whistles, and most people couldn't understand how to use all these different things effectively to get on with their job. So, for example, there were no reserved words, but they did have the names date and time, but that didn't work out. That has a story associated with it. And then there were new attribute statements and statement options that could be added to PL1. But if, then, else, and do were not reserved, okay, here. So you'd start to wonder if they didn't use these, then what in the world is going on? Because these are things that most programmers are quite familiar with. But the idea was that each capability had to be independent of the other capabilities. The exception handling capabilities kicked in at runtime, which was a problem. And the programs were broken down into macros, which led to all kinds of separate binding issues here, and the debugging facilities were all integrated in the language, which was nice, but not, at the end of the day, not that useful. So that was PL1, something that could have taken off but didn't. Now we go to BASIC, which did take off. This is beginner's all-purpose symbolic instruction code, BASIC, B-A-S-I-C, which is general purpose, high-level programming language designed for ease of use. Ease of use typically wins over any other attribute that you'll come up with. If it's easy to do, people will do it. If it's hard to do, they won't do it. So John Keamany was the actual president. He was in the Dartmouth math department, but he wanted the students all to be able to be exposed to and use computers. And so all the students at Dartmouth were using this Dartmouth time sharing system, and they could run and they could edit, they could compose and run BASIC programs on all kinds of terminals all across the campus. And so that's what they did. And many earlier video games trace their history to a version of BASIC here. It's going to live on forever, don't worry. This encouraged multiple BASIC dialects. So Microsoft developed BASIC in 1975 for this very first personal computer in Albuquerque, New Mexico, with Paul Alan and Bill Gates. And this thing was called Tiny Basic because the amount of memory they could afford for this was typically something like 4 kilobytes. And so you want to have the basic language software taking up as little of the space as possible so you can run your application, say a game of some sort. But the end result of this was that virtually every home computer that emerged in the late 1970s had a basic interpreter installed by default on it. And it declined in popularity in the 90s as there were more powerful computers that came to market and had more advanced features, such as Pascal and C, that made things possible that BASIC couldn't do. But that's to take nothing away from BASIC. In fact, in '91, Gates pushed Microsoft to release Visual Basic. So they updated BASIC to have a visual forms filter. And this is still running around today because Microsoft is driving it. The thing to keep in mind here is that Kemeny did all this at Dartmouth on the cheap, ended up just deciding that the students had to learn about programming, and the best way to do it was to give everyone access to a terminal and get them to write programs. And including English students or students in Latin. This is Dartmouth, and so it goes. So it's still there, and it's very it'll live on forever. There's Kemeny himself actually wrote the first version of BASIC, and it was heavily FORTRAN after a dialect of FORTRAN and so forth. And there were things there that made it easy for people to understand. If they understood FORTRAN, you can understand BASIC. But BASIC was meant to be simpler, easier to use, and people could do things very quickly, more quickly than they could in FORTRAN. Now we come to C, which is a general purpose programming language developed at Bell Laboratories by Dennis Ritchie. It remains widely used today. C actually is the successor to the language B, surprise, surprise. And what happened here was that Dennis Ritchie and Ken Thompson developed an operating system called Unix. Thompson did this entirely in PDP, DEC PDP 11 assembler, and it was all great, but they realized that for this to really go anywhere, they'd have to not have it implemented in assembler, but implemented in a higher level language. But still, it had to preserve the capabilities of assembler in the sense of being very fast and efficient. And you wanted to be able to interface to the hardware and writing device drivers and so forth. And so C includes, well, it's called the general purpose language. It includes the capabilities to mask on a set of bits in a register. And so you can see that most high-level languages wouldn't include this as a capability, but if you're doing this so you can write a device driver, or you can do something that would be kernel level programming that would be critical to the operating system functioning or not functioning, as the case may be, then you see the power of C, and so it goes. So after some arm wrestling and so forth, in 72, 73, Dennis Ritchie developed C. Again, they went ahead and implemented Unix in C. It was, again, as I said, written entirely in assembler. And this really led to things taking off at that point. Thompson took a sabbatical in 1975 and went to Berkeley, and he took a tape with Unix on it and C, and there was a very capable person there, Bill Joy, at Berkeley, who grabbed this and ran with it and was doing all kinds of amazing things there with this. And this then spread all over Silicon Valley. So it resulted in all of these companies were building computers, but they didn't have any real operating system. And here was Unix that was coming out of Berkeley, right across the bay from Silicon Valley. And so many companies picked it up. And the end result of all this was it spread all over the place. One of the unforeseen outcomes of this was that there were two dialects of Unix, iOS, which is the Apple operating system for Macintosh and for its iPhones, and Android for non-Apple mobile phones. And so you can see that C lives on in all of these phones that we have in our hands today. And so it goes. So C is an imperative procedural language. It's designed to be compiled to provide low-level access to memory. I gave you an example of this, and yet it also supports pointers and has a wide variety of what would be considered to be high-level functions here, make it a very flexible, useful programming language. Since the year 2000, C has consistently been ranked among the top 3 languages in popularity of all programming languages. The other thing to keep in mind here is that there's the language has a small fixed number of key words. So there's if, else, for, do, while, and switch, and that's kind of it. But that control gives you the flow of control throughout the program. And there's all kinds of operators that are here, and you can have more than one assignment in a single statement. That was one of the problems with BASIC, was one statement, one function, that's it. So we had support for functions here, data typing. There's heterogeneous data types that allowed related data elements to be accessed and assigned its unit. And then there was a union function. Array indexing is a secondary notation defined in terms of pointer arithmetic. And this is where people can really wipe out in terms of writing code, where the pointers end up being pointed to nowhere, or they leave the pointer in place and it corrupts memory because people forgot to get rid of the pointer. The other side of things with C is it's basically modular, because files are compiled and linked together that are visible to all the other files. In fact, in Unix, there's a capability for stringing files together called pipes, which is a pipe is a buffer that takes the output from one function, feeds it as the input to the next function. So you can take modules and just run things together through a series of pipes to end up with a very complex application in a very short period of time. But you know, one of the problems with C is it doesn't include features found in other object-oriented languages, and it doesn't do a good job on garbage collection. These are clearly can be implemented or emulated through external libraries, and that's what people have done. But there's other alternatives to this, one of which is evolving C into C++, which is actually intended to be an object-oriented language, the object-oriented version of C here, but it's meant to capture a lot of the capabilities and good features that people liked about C. And it's out there, and there's a wide variety of people using it. It's found in video games, desktop applications, all kinds of servers on the web, and even mission critical applications like space probes. Here's a different thing, MatLab. This is really widely used by all kinds of engineers, chemical engineers, mechanical engineers, electrical engineers, software engineers, as opposed to electrical hardware engineers. MatLab is a proprietary programming language that was really developed to allow matrix manipulations, but it just blossomed into a whole bunch of toolboxes for doing all kinds of things that are of interest to real engineers. And most engineers don't even realize that the MATLAB programming language is in fact an object-oriented programming language. And there's probably over 5,000 colleges and universities around planet Earth that use MATLAB in carrying out research and instruction, not a small feat. It also has some interesting graphics capabilities. So Cleve Moeller, who's shown here, developed all this and proselytized it, and it just took off. And by the time people realized what was going on, he had this company, and he marketed and supported this, and the rest is history. In the 1980s, MATLAB got reprogrammed in C as opposed to its own language, and this led to the creation of the MATLAB programming language and all of the toolboxes that are out there today. Java, which is a high-level class-based object-oriented programming language, was designed to have as few implementation dependencies as possible. And it's meant to be run anywhere. The Java applications are typically compiled as byte codes that can run on any Java virtual machine, regardless of the underlying computer architecture. So the syntax is similar to C and C++, but it simply has fewer low-level facilities in either one of them, which, having said that, these Java virtual machines are everywhere, billions of them out there doing all kinds of things. And so what happened was it gained a lot of popularity when it first came out. And, according to one survey, was the third most popular programming language in 2022. But there's other languages coming on that use these Java virtual machines, but are not written in Java. And so it goes. So we'll go on to Python. Python is a high-level general-purpose programming language with a design philosophy that emphasizes code readability, and it's also dynamically typed, and it includes garbage collection, which is one of the problems that you run into with C and C++. It supports multiple programming paradigms such as procedural and object-oriented and functional, and it's often described as all the batteries are included due to its very comprehensive standard library. So Python ranks as one of the most popular programming languages on planet Earth, and has gained a widespread use in artificial intelligence. It's a relatively recent language compared to these other ones, because it was implemented in December of 1989, and it took several years, but here it is today. We're up to release 2.0 in the year 2000, all kinds of new features and people using it. There was at least 3.0 in 2008, and The test of all these things is if it's being used, then that means that people find things in it that they can't do with other languages, and Python is the example of that. That brings us to our final one, Rust, which is a general purpose programming language that really emphasizes performance, but type safety and supports concurrency. It enforces memory safety so that you don't scribble all over memory. You don't have references that point to the same or to invalid memory locations that don't exist. And there's no garbage collector here. So to enforce this memory safety, its borrow checker tracks the object lifetime of all references in a program during compiling. And in doing so, it'll spot if there's any errors and will take it away from there. But it doesn't enforce any programming paradigm type, but it'll support object-oriented programming as well as functional programming as well. So this is coming on strong, and it became the first language in December of 2022, other than C and assembler, to be supported in the development of the Linux kernel, which is the thing that runs on the internet servers. It's been noted for very rapid adoption, and we'll expect to see it used more going forward in time. The key focus on this was memory safety, concurrency, the ecosystem that comes with this is all kinds of libraries or crates that are available here for doing all kinds of things. Very powerful error handling, and then a very low, very small runtime footprint. So it can run on embedded systems, Internet of Things devices, microcontrollers, etc. That's it. So thank you very much, and we'll take it from there. All the best.